Okay. Let me see. Can you guys hear me?
Yes.
Okay. So great to be back here, MLconf. And today I'm going to be talking about, it was great to give this talk after the first two talks, which were awesome. And we use factorization machines. We use tensor factorizations. We hire people that are great at each of these two techniques or many others. I've actually published myself on tensor factorizations in the past. But the question I'm going to try to answer here is like, what do you do when you're in a company like Netflix and you know how to do all these things, but what are the things that really matter and how do you address your priorities? What matters, what doesn't matter? How do you deal with your data and your algorithms? And I try to formulate it as 10 little lessons or big lessons that we've learned over years of building machine learning systems at Netflix. And before I get into that, I'll spend just a couple of minutes telling you a couple of numbers about and the things that we do at Netflix and how important it is for us to think about machine learning algorithms. This is something that came out in an article last year, which I thought reflected very well how we think about the importance of our algorithms at Netflix, right? As you can read here, we think, or that was the headline, that our algorithms know you better than you do yourself. What this was referring to, it's a very interesting case. We have a feature in our product that is called My List. That feature allows users to actually bookmark and put things that they think they're going to watch in the future. And before we rolled this feature out, what happened is that we allowed users to sort things themselves, so they could put however much time they wanted into sorting their things and saying, okay, I'm going to watch this first, I'm going to watch this second. This was actually kind of a legacy from the DVD world, where you really wanted to put a lot of attention in what DVD you got next weekend and what DVD you would get afterwards. So what was happening there is that we saw that people kept adding things to their list. They might put some time in sorting them, but at the end they weren't watching them. So what we decided to do is say, okay, forget the users and the way they sort them, let's give them an algorithm, and let's give them what we think they would watch, and this was a positive. So we kind of proved that in some cases you can make algorithms understand you better than you do yourself, right? So that's the point that we were trying, this article was trying to make. So machine learning at Netflix scale, we have over 50 million members in 40 countries, more than 1,000 device types. The latest number, 7 billion hours in Q2 of this year, which basically roughly translate into 7 million plays a day, 4 million searches a day, 6 million ratings a day, a total of over 100 billion events that we're logging every day, and as you probably know, over 30% of peak traffic in the US. And of course, now we're also growing in all the other 40 countries. And we use a ton of smart models at Netflix, right? So here's a list of things that we use, as I said before, including factorization machine and tensor factorizations. And people try to, or often simplify Netflix as the Netflix prize and what we did there. And we've talked about, we use SVD-style matrix factorization and restricted Boltzmann machines for rating prediction, but we do many other things that are not rating predictions. We do ranking, we do page optimization, and I've talked about that in the past. And these are the kind of things that we do. So how do we think about doing all of this, and how do we think about the things that matter and the things that don't matter? So I'll try to formulate that in 10 lessons again, and I'm going to go quickly over them, so I won't have time to go into much detail, so please grab me afterwards over coffee or lunch, and I'll answer as many questions as you have. Okay, the first one is about this idea or this discussion that it's been going on for a long time about do you really need more data? Do you need better models? A lot of data trumps better models. What's going on here? And I try to think about it in a different way. It's not about either or, it's about and, right? It's about doing both, and sometimes some things matter and sometimes some things don't matter so much. A couple of thought points that you might want to keep in mind and interesting stories. The first one is about a blog post that appeared during the first year of the Netflix prize. So there was a blog post by Anand Rajaraman, who at that point was teaching a data mining class at Stanford, and he posted this post here with the title of "More Data Usually Beats Algorithms." What he was explaining in this post is how some of his students had improve some of the results in the Netflix prize at that point, again, first year, by adding some metadata that they were getting from IMDb. So the point that he was trying to make is like, well, if you add metadata to the ratings that are provided with the Netflix prize, you're going to increase your accuracy, and you don't really need to think too much about algorithms. It's all about dumping in more data. Now, the truth is that that was not the case. A few years later, actually after the Netflix prize finished, some of the people working on some of the leading teams published this other paper where they were saying that even a few ratings are more valuable than metadata. So they were basically debunking that blog post, doing the exact same thing, actually adding metadata from IMDb, and proving that if your algorithm is sufficiently optimized for the ratings, like the ones that had won the Netflix prize, really adding metadata didn't help. So the point here is that just adding a few ratings was more useful than a ton of metadata that you could get from IMDb. By the way, my point that I'm trying to claim here is not that content metadata is not useful for rating prediction. I'm just trying to say that sometimes you can tune your algorithm in such a way that adding more data is not going to be so helpful. So sometimes it's not only about more data. Another point that people try to make is, well, it might not be about adding more features or different features, but the truth is you do need more training examples in your data set. That's always going to help. And that's this famous paper from 2001 by Banco and Brill, where they were showing that really some very different prediction algorithms, from naive Bayes to a perceptron, they were basically behaving the same, and they were following the same kind of trajectory as you kept adding data samples into a language prediction problem. So, and this was picked up by Norvig in this article on the unreasonable effectiveness of data, and Norvig himself was quoted saying that Google has more data and that's why it's better. It's not about algorithms. So is this really true? Is it about adding more samples to your data? Well, the thing to keep in mind here is these models are low bias models. They have millions of parameters. Actually, these are language models, so basically the size of your model is going to be the size of your vocabulary. So yes, in this case, adding more data, adding more samples is likely going to help, but that's not always the case, right? So to give you a counterexample, this is the accuracy that we get from a model that is in production at Netflix. It doesn't matter which one it is, but in this model, what we see is that as soon as we go over 2 million training examples, it's completely flat, right? And the reason for that is, well, you don't have as much complexity in the model, you don't have as many parameters. With this amount of data, you're done. You don't need more training examples. So yeah, sometimes it's not about adding more data, right? So that's my first lesson. And actually, I'm gonna, the following 2 or 3 lessons are kind of like writing on the same story about big data versus models and which one is better. So the second one is, as we saw before, you might not need all your big data, right? So everybody has big data nowadays, and the question is, do you really need that big data? And it's very tempting to say, oh, I have such big data, a lot of data coming in, let me throw it all in. You know, it won't hurt. Well, it might not hurt, but you might not need it, and you might be putting too much attention on things that are not important for you. So to give you an example, you might have millions of users, but if you're trying to estimate 100 factors of a matrix factorization problem, do you really need all those millions of users? Well, maybe not. Maybe with sampling some of those users, they're going to be representing enough the different 100 factors that you're trying to come up with from your matrix factorization, and you're going to reduce complexity, and you don't need to go into this high-scale distributed matrix factorization solution. Now, in order to do that, you need to be smart about how you choose your samples, right? So you might need to do something like stratified sampling, because of course, it might be tempting to say in the matrix factorization example, you could say something like, well, because I don't want all my users, but I want my metrics not to be very sparse, I'll get the users that have more ratings. Well, that might not be a good idea, because the users that have more ratings might be representing users that have been in the system for a very long time, who have one particular kind of behavior, and they're not representing well all the different behaviors that you're really trying to come up when you're doing the factorization. So you might need to be smart about how you stratify your sample. Okay, number 3. The fact that a more complex model doesn't work or doesn't improve things doesn't mean that you don't need a more complex model. What does this mean? So imagine the following scenario. You've had a linear model in production. It's been working great. You've been optimizing features for that model for a long time, and things keep improving little by little. And then all of a sudden you say, yeah, you know what? I'm going to try a more complex model, a nonlinear model that is going to beat the previous one because obviously it's better. Well, and that doesn't work. Or it could be the other way around. You might be using that simple linear model that you've had in production and say, oh, now I'm going to add this very complex feature that has some nonlinear behavior, and that doesn't improve things. So what's the lesson here? Well, the lesson here is that both things are connected and they're very related. So if you add more complex features, you might need a more complex model that is actually able to learn those features. And the other way around, if you are changing your model and making it more complex, the previous feature set that you were using, which was actually engineered for the linear model, it's not going to be useful. So you better then turn your features into whatever the new model is going to understand or it's going to be able to leverage. Right? Okay, number 4, be thoughtful about your training data. Again, another example. Imagine that you're training a textbook binary classifier. First thing you need to know, define your positive and your negative examples, right? And that seems so trivial. You know, this is my class, these are positive and these are negatives. Well, in real life, it's not so easy to define what a positive is and what a negative is. And you need to put thought into that because that's going to impact the kind of model that you learn. Just to give you a couple of examples, in the Netflix case, here's a question, right? Is this a positive or a negative? So a few examples. A user watches a movie to completion, but then rates it 1 star. Does that mean that that's a positive? A user watches the same movie again, maybe because didn't find anything else. User abandons movie after 5 minutes. Is that a positive? Well, probably that's a negative. What about 15 minutes? What about an hour? The user starts watching a TV show, but then abandons the TV show after 1 episode, or maybe 2 episodes, or maybe watches only the first season, but doesn't continue with the second season. Is that a positive or is that negative? And so on, right? So you could find examples in real life where even a seemingly very easy to task like defining a binary classification problem, it's not so much. There are many other issues that you need to be aware when defining your training set, and one of them, just to give you an example, is what we like to call time traveling. This was a term coined by Justin, who is over there in the audience. So time traveling, we define it, this is not a textbook definition, this is a very practical definition, as the usage of features that originated after the event that you're trying to predict, right? So an trivial one that I have here in the example is you're trying to predict whether the user will watch or won't watch a movie, and one of the features happens to be the ratings. Of course, if you use the rating of a movie and you know the user rated the movie, well, chances are the user watched the movie, right? So it's a highly predictive event because it actually originated after the user watched the movie. And that's a very trivial example, so it's clear to say, okay, yeah, you need to only get the ratings before the event of watching happened. But the truth is, when you're in production and you have a complicated or complex feature data set that comes from different combinations, from different places and so on, going into this time traveling problem happens more often than not. And whenever we have somebody in the team coming in and yelling that he got a huge improvement in one of our prediction problems, the first question we ask, like, are you sure you're not time traveling? Okay, next. Learn to deal with the curse of presentation bias. So if you think about presenting some results in a page or in anywhere that you're presenting, you'll see a pattern like this where a user is most likely to click or to watch or to do some action on the things that are shown in one position of the page or another, right? And that's well known, and that's something that you do need to learn to cope with. Otherwise, your models are not going to work, right? So users are only going to click on whatever you show, and the problem is that there's a kind of like a difficult situation here, because you cannot decide that what you're showing to the user and the user did not click on is bad, because that's something that your model decided that was good. So you can't have your model fight against itself continuously, right? So, for example, deciding that everything that you showed and the user didn't click on is a negative, that's probably not a good idea, because the user did not watch that movie today, maybe because he was watching a TV show and he wanted to finish the TV show, but it's not that he didn't like that movie. Yeah, that movie is good, but I'll watch it next week, right? So you have to be smart about how to figure out how to feed that presentation bias in some way, and correcting, for example, correcting for the probability the user will click on a given position, having this idea of attention models of the users, that's a good idea, right? So if the user went all the way down to position in a page that is very unlikely and clicked on something, that's a really strong positive, right? The user really wanted to watch that. And explore-exploit approaches such as multi-arm bandits are also a good idea to deal with this bias. Okay, number 6, the UI is the algorithm's only communication channel with that matters most, which is your users. And this is related to the presentation bias. I was kind of, lesson number 5 was kind of putting it in a negative way, but here I'm trying to put it in a positive way. So the UI is good, and you have to live with the UI and learn to cope with what the UI offers you and what you need to give back to the UI, right? So think about the feedback loop. The UI generates everything that is going to go into the algorithm. The user clicks, the user scrolling somewhere, the user seeing something. All those logs are going to be data that's going to be feeding back into your algorithms. And at the same time, it is going to be the place where you are showing the results of your algorithms, right? So thinking about this holistically, it's going to help you. And for example, something to keep in mind is that, just as I was saying, that changing the models and the data and the features is something that needs to go hand in hand. Changing the algorithms and the UI is also something that needs to go hand in hand. If you optimize your algorithm for a given UI and you change the UI, well, you need to adapt your algorithms again, right? Among other things, because your attention models that you had before changed, for example. And we do that all the time. Many of the A/B tests that we run at Netflix, which are changing UI components, they have an algorithmic component to them that is adapting to this new change, and the other way around. Okay, number 7. Data and models are great, but you know what's better? The right evaluation approach. So if you do great with your data, you do great with your models, but you don't know what you're measuring and what you're optimizing for, you're basically shooting in the dark. So you don't know what whether that's going to matter at all. So we try to think about this sort of dual experimentation process where we have an offline component and an online component. In the offline component, we start with a hypothesis, and we basically use offline metrics, and we iterate on those offline metrics until we have something that is worth testing. And on the online side, we do A/B test, and we take whatever we did in the offline side, and we show it to users, and we then feed that back into our offline experimentation process. So in the case of the online component, in the case of the online component, a couple of things. It's important that the decisions on the product are, most of them, data-driven. And this can only be done if you have a very clear statement of what's called the OEC, right? The overall evaluation criteria. In our case, in Netflix, that's member retention, and we're lucky that we have a very easy or crisp measure, which is like, well, if you decide to pay at the end of the month, it means that you like our service. And if you can change that, it's a great thing. And you actually can change that by improving an algorithm, right? Usually, the most effective OECs are long-term metrics, right? Things that need some time to be measured, like retention. There's a problem with them, is that, well, they're long-term, so you need to wait some time to finish that iteration. So yes, you might need to have short-term metrics that you're optimizing, and they're proxies to what you really care about, and you can use as information to do faster decisions, but you have to be careful because they're not always aligned to your OEC. So the offline part, you're going to have a ton of different offline metrics that they're easy to implement, and you can measure them, and they're going to be telling you different things. For example, here you can't really see, but here what I'm plotting is 3 different ranking metrics, MRR, NDCG, and fraction of concordant pairs, and each of those metrics has a different characteristic, meaning that they will weight more the head of the ranking, the middle of the ranking, or they'll be just flat. And of course, they're going to be telling you different things. So you better know what the differences are, because otherwise you might be optimizing for the wrong thing, because your UI might be showing only the head of your ranking, or might be showing a longer part of your ranking. So that's going to matter here. Again, as I said before, offline performance is used only, it's an important part because it allows you to do a lot of experiments that are cheap in your machines before you actually need to allocate more expensive A/B tests. So, but it only informs you of what A/B tests make sense, but you really are going to have to make your decisions based on your final OEC. And a critical and mostly unsolved, although a lot of people like ourselves and Netflix are working on it, is how to find a good model that correlates those offline metrics to the online ones, right? And you can do things about them, and you can build regression models from one to the other, but it's not a trivial task. Okay, number 8, distributing algorithms is important, but it's also important to know at what level to do it, right? So, yeah, let's say that you finally decided that you need to use more data that you can fit in one core, one machine. Now, what do you do, and how do you do it? And I usually talk, there's a blog post, by the way, that we did about this, about 3 different levels of distribution or parallelization. The first one is for each subset of the population, for example, region. The second one is for each combination of the hyperparameters. And the third one is for each subset of the training data. So what this means is, in the case of Netflix, we might have a model that is operating in different regions of the world, and we have the US, and we have Europe, and we have Latin America, and we have many different regions. And it might turn out that we decide that we want to optimize a different model for each region. Well, that's an easy thing to do, because you don't really need to pass data from one region to the other unless you want to share some information. And you can just basically go and train things separately, no communication needed, no data transfer needed. The second one is a little bit more involved. It's for each combination of the hyperparameters, right? So imagine that you're training different values of the hyperparameters because you're retraining a model and you want to pick the best optimal combination of those hyperparameters. Now, in that particular case, you can completely distribute the training, but you do need to share the data, right? You have some data that you want to send to different machines, and you can then optimize independently, and you have to share, obviously, the findings of like this combination of hyperparameters work better than the one that I had in this other machine, and you can do that in different ways. But you only need to communicate data and values of hyperparameters. And the third one is the one that is more involved, and that's the one that people talk mostly about when they talk about distributing machine learning, and it's great, but my point is there are easier things that you can do before getting into the third one. And the third one, yes, you can address it in the case of distributed computing by doing ADMM, for example, or you can do multi-core like Hawkwile, or you can use your GPU, sorry. And actually, so this another blog post you can read about is how did we do distributed neural network training on GPUs in the Amazon cloud. And here we were actually doing the 3 levels of distribution, and we were using, in this case, we were using experiment. We weren't using Mo yet, although there is a talk, the last talk of the day, I'm going to plug, Scott Clark from Yelp is going to be talking about Mo, which actually can do this piece here. And then, so that's how we're doing the level 2 distribution. And then the level 3, we're actually doing at the GPU level because we're using GPU implementation of the neural network stuff. Okay, almost running out of time. Number 9, it pays off to be smart about choosing your hyperparameters. So you can automate the choosing of your hyperparameter values. And again, the talk about Mo will probably go into some things like Bayesian optimization using Gaussian processes, which is something that's interesting and you should probably try out. But the question that I'm addressing here, is it enough to just choose the best value that your hyperparameter is going to give you according to your optimization metric? And for example, is a regularization lambda of 0 better than a lambda of 1,000 if that decreases your metric by only 1%? And the answer is probably not, right? If your lambda is 0, you're probably overfitting. So you probably want to go to a higher lambda, even though your validation metric is showing you some decrease. Of course, you can then use the test set to decide what's good or bad. But if you're only optimizing on your validation set, your best bet is to go for the highest lambda that gives you a result that is at least on a margin of noise of the metric that you're trying to optimize. And the margin of noise is something that you can define, of course. It could be 1%, could be 2%. You have ways of figuring that out. Okay, and the last one, there are things that you can do offline, there are things you can't, and there's nearline for everything in between. Another blog post that you can search for that we publish in our team that actually explains this whole picture of what you can do offline, what you can do nearline, and what you can do online. And it's really, I mean, this process of thinking what matters and what matters to do online, because that's going to be more costly, of course, if you need to do it online and real time, versus what you can put on the offline part, which you can do much more complicated things with much more data. It's a very interesting process that really pays off. I'm just going to give, short of time, I'm just going to give a quick example. So in the matrix factorization example, again, you can do something like, let's use whatever users we decided to use to compute our matrix factorization. Let's do the offline computation for the item vectors. And that's something that you can do, you know, with then as much data as you need. You don't need to be worried about doing it very quickly. You can just, you know, take your time. It takes you a day, whatever you need. It depends on your problem, of course. If you're trying to recommend news, maybe you need to do it faster. But you can probably take more time in computing your item factors, and you can do that as an offline batch process. But then, when you're computing your user factors, you can actually solve them online, and you can separate both things, right? Once you have your item factors, you can compute your user factors, and all you need to do is solve an equation which you can solve in milliseconds pretty easily for a given user. So separating your problem into what you can do offline and what you need to do online is a very important thing. Okay, so I'm done. As a way of concluding sort of like those 10 lessons put into 4 sort of like shorter takeaway messages. 1, choose the right metric. 2, be thoughtful about your data. 3, understand dependencies between data and model. And 4, optimize, but optimize only that matters. Again, I'll be over coffee and lunch. I'll be happy to take as many questions as you have.